Hi everyone, myself MGV Sai Teja, bearing roll number 24BQ1A04A2 from VVITU in the Department of ECE. Today I want to tell the seminar topic about JFET drain and transfer characteristics. Introduction to junction field. Effect of transistor. What are JFETs? Junction field effect transistors are voltage controlled semiconductor devices that regulate current flow through a conducting channel. Unlike bipolar junction transistor, JFETs control using an electric field rather than current injection. Why JFETs matter? JFETs offer high input impedance, low noise characteristics, and excellent thermal stability. These properties make them indispensable in applications such as low noise amplifiers, switching circuits, voltage controlled resistors, and precision analog front end design. This is the introduction of the junction field effect transistor. Understanding JFET construction. There are mainly three structures: physical structure, operating principle, devices types. In physical structure, a JFET consists of a semiconductor channel N-type or P-type with two ohmic contacts, the source and drain. A PN junction gate surrounds the channel, controlling current flow through depletion region modulation. And the next one is operating principle. Whenever reverse bias is applied to the gate channel junction, a depletion region forms. This region narrows the conducting channel. The region narrows the conducting channel, increasing resistance and reducing drain current, the fundamental principle of voltage controlled operation. Next one, devices types. JFETs comes in two configurations: N channel electrons as majority carriers and P channel holes as majority carriers. N channel JFETs are more common due to higher electron mobility. Drain characteristics. ID versus VDS relationship. The drain characteristics illustrate how drain current ID varies with the drain source voltage for different gate source voltages. This relationship reveals three distinct operating regions that define JFET behavior in circuits. First one, ohmic region. For low VDS, the JFET acts as a voltage control resistor with linear ID VDS characteristics. Saturation region. Beyond pinch off voltage, ID becomes nearly constant, making this region ideal for amplification. Breakdown region. At excessive VDS, avalanche breakdown occurs, causing rapid current increase with and potential device damage. Key parameters for drain characteristics. IDSS, saturation drain current. The maximum drain current when VGS equal to 0 volt, representing the JFET's maximum current handling capability. This parameter typically ranges from 2 mA to 20 mA depending on device specification. VP, pinch off voltage, the gate source voltage at which the channel becomes completely depleted and drain current approaches 0. Typical values ranges from -2 volt to -8 volt for N channel JFETs. Saturation region behavior. In saturation region, the JFET operates as a constant current source. The drain current remains relatively independent of VDS, controlled primarily by VGS. This characteristic make JFETs as excellent for amplifier applications, providing high output impedance and stable gain. Transfer characteristics. ID versus VGS relationship. Understanding the transfer curve. The transfer characteristics show how drain current varies with gate source voltage whilst maintaining constant VDS. This parabolic relationship is fundamental to understanding JFET behavior in amplification and switching applications. The curve demonstrates that as VGS become more negative for N channel, the drain current decreases progressively until reaching pinch off. This nonlinear relationship defines the JFET's transconductance properties. As we saw the graph, ID taken along the y-axis and VGS taken along the x-axis. The Key observation of transfer characteristics provides direct insight into device transconductance, operating point selection, and small signal gain prediction for amplifier design. Mathematical analysis and transconductance Shockley's equation. The relationship between drain current and gate source voltage is precisely described by Shockley's equation, which forms the mathematical foundation for JFET analysis. ID equal to IDSS of 1 minus VGS by VP whole square. The quadratic equation accurately predicts JFET behavior in the saturation region, where most amplifier applications operate. Transconductance derivation. Transconductance measure how efficiently the voltage controlled drain current, a crucial parameter for amplifier gain calculation. GM equal to dou ID by dou VGS, that equal to minus 2I DSS by Vp of 1 minus VGS by Vp. At VGS equal to 0, transconductance reaches its maximum value. Gm 0 equal to minus 2 IDSS by Vp. This parameter directly determines the voltage gain achievable in JFET amplifier configuration. Practical application in amplifier design. Common source amplifier. The most popular JFET configuration offering high voltage gain and moderate input impedance. Drain characteristics determine the optimal bias point, whilst transfer characteristics predict again. Source follower buffer utilizes JFET's high input transfer character ensure unity gain with minimal distortion, making it ideal for interfacing high impedance sources. Cascade configuration combines common source and common gate stages for enhanced bandwidth and a reduced Miller effect. Drain characteristics optimize both device operating points for maximum performance. Experimental setup and measurement techniques. Equipment required for characterization. DC power supply. Two variable DC sources, one for VDS 0 to 20 volt, another for VGS minus 10 volt to 0 volt, with fine voltage control capability. Precision multimeter. Digital multimeter for measuring drain current, typically 0 to 100 milliampere range, and voltage parameters with at least 0.1% accuracy. Automated curve tracer. Automated instrument that plots characteristic curves directly, enabling rapid characterization and parameter extraction. Measurement procedure. Drain characteristics. Fix VGS varies VDS from 0 to breakdown record ID. Repeat for multiple VGS values. Transfer character. Fix VDS in saturation. Vary VGS from 0 to pinch off record ID value. Data analysis. Plot curves. Extract IDSS VP and calculate transconductance from slopes. Comparative analysis and design consideration. JFET versus other transition type. Input impedance, noise performance, gain, switching speed. It indicates some colors. Design guidelines. Select JFETs with IDSS matching circuit current requirement. Ensure VP allows adequate gate voltage swing or signal handling. Consider temperature coefficient for stable biasing across operating conditions. Verify transconductance values meet gain specification for amplifier applications. Advantage of JFET: very high input impedance, low noise, no minority carriers recombination, good thermal stability, simple construction, low power consumption. Applications of JFET: amplifier due to high input impedance, analog switches, voltage control resistors, buffer stages, oscillators, RF circuits, current limiters, pinch off regions. Summary: JFET is voltage controlled high input impedance device where the width of the channel is controlled by the reverse biased gate voltage. It works in ohmic pinch off and cutoff regions and follows the square law relationship between ID and VGS because of its low noise and simple design. It is widely used in amplifiers, switching, and signal processing applications. If you want, I can also provide JFET characteristics diagram, JFET formulas. So this is the JFET drain and transfer characteristics we discussed in this PPT. Thank you for giving to represent my PPT in this. This is the end of my PPT.